Hello wizards! Let us learn how we can make the data lit with the help of logistic regression. Oh, yet another regression. I'm just done with the linear regression. Okay, come on, let's see how this is different. But where do I even start? I strongly encourage all of you to understand about linear regression and gradient descent before even you start with this video. Siraj and Colin have very good videos on those topics. Okay, what can we do with it? Simply, we can use the help of logistic regression to predict whether an email is spam or not. Isn't it cool? We can shield all the spam that is coming to our email. Oh, this is how we started with logistic regression. And still, we are using logistic regression for many of these classification use cases. In logistic regression, predictions are discrete. That means only specific values or categories are allowed. We can also view probability scores underlying the model's classification. There are three types of predictions that we can do with logistic regression. First one, the binary. So we can predict if the output is pass or fail, spam or not, those kind of things. In multi-classes, what we can do is we can predict cats, dogs, sheep, which are not even connected to each other exactly, but we can try to predict what they are. That's what we can do with multi-class. Ordinal is something where the output is in order. For example, tall, taller, tallest, or low, medium, high. These are the things that we can do with the help of logistic regression. Oh yeah, as I said before, logistic regression is a classification algorithm. What? Regression for classification? Let's see how it is possible. So, we can say linear regression and logistic regression are connected in many ways. We must know the differences before we say where we should use linear regression and where we should use logistic regression. Let's see how linear regression is different from logistic regression. It's very simple. In linear regression, we have a line that differentiates the outcome, where in logistic regression, we have a curve. Okay? Oh yeah, this sounds simple, but there is a lot of math involved in here, and let's see how the math is going to help us differentiate these things and why this is being done. Let us flash back into the basics. Okay? So let's see what probability is, or let us remind us what probability is. Probability is the measure of the likelihood that an event will occur. For example, probability quantifies as a number between 0 and 1. So, if we get 0, that indicates impossibility and 1 indicates certainty. Let's see few examples. I'm flipping a coin. I may either get heads or tails. So the probability for me to get a head is 1 by 2, that's 0.5. 50% of the time I may get a head or I may get a tail for the rest of the 50%. So if we take a die roll, I may get from numbers 1 to 6. What is the probability of getting 1 or 2 out of those 6? So it is 2 divided by 6. So we get 33%. In the example of playing cards, what is the probability that I will get a diamond card? So in a deck of cards, there can be 13 diamond cards, and what is the probability that I will get one of them? So it is 13 divided by 52, so which is 0.25. 25% of the time I may get a diamond card, right? So this is probability. Now let's move forward to see what are the odds. So if you remember this from the Star Wars movie, our favorite C-3PO is letting our friend Han Solo know that his chances are nearly impossible. So he says, never tell me the odds. I guess now you will get an idea of what an odd is. Let's see. So odd is the probability of occurring versus the probability of something not occurring. So we could say probability divided by 1 minus probability, that is the yes or no. So if I flip the same coin again, the probability of me getting heads is 0.5 but the odds are 1 is to 1. I may either get a head or a tail. So in our next example, for the probability for me to get 1 or 2 when I roll a die is 1 by 2. 50% of the time it may happen. That's the odd. The same goes with the playing card example. Let's see about two new functions, a logit function and a sigmoid function, and how this can help us differentiate between linear regression and logistic regression. The logit function is simply the algorithm of the odds. So logit of x will give us log of x divided by 1 minus x. So if we see the plot here for the logit function, how we can see something like an yes, but this is not what we want for our logistic regression. So we have to use the inverse of the logit function, which is known as the sigmoid function. That is, if you have a probability p, the sigmoid of the logit of p will give you the p. So here a plot of sigmoid function will show you the difference between a logit function and sigmoid function. How we are using the logit function to convert it into a inverted yes, which will give us more clear picture of what we need and how we can transform the line in a linear regression to an S curve for our logistic regression. Now let's see the math behind it. So logit can be also represented by log of the odds. So the log of p divided by 1 minus p. Whereas the sigmoid is expressed by a formula 1 divided by 1 plus e to the power of minus alpha. So what is the alpha here? So if you remind what you have learned in the linear regression, you will be able to correlate that here. So the alpha will be given by the beta that starts with 0 plus beta 1 into its weight x1, and it goes to so far for all the independent variables that we have got in the data set. So the alpha can be also denoted as the natural ln of p divided by 1 minus p. What is the difference between log and natural ln? Let's remind it again. So log have the base value of 10, whereas ln have the base value of an e. So that's the difference. Here the sigmoid function maps arbitrary real values back to the range of 0 to 1. The larger the value, the closer to 1 you will get. That means certainty. Wow, let's get into code. How we can code this sigmoid function in Python? So we have to import the library called math. Then we are defining a class here, sigmoid of x. So when we give the x value, it will return the sigmoid value for that particular x. So 1 divided by 1 plus math of exponential of minus x. We also have few implementations that is defined in few of the libraries where we can easily get the sigmoid function. For example, SciPy library have got this stat function from where you can borrow the CDF function to get the sigmoid. And it also have a special set of functions which gives the expect, which is nothing but sigmoid. It is the inverse of logit function. So now we have three different functions which can give us the same value as you see above. But what's the difference between these three? So here, if I time it, we can see that our own sigmoid function takes very less amount of time to process than the rest. Why is that? Isn't the library supposed to be more good? Yes, they are. What we have done is we are just looking for only one value here, but those libraries are optimized to do the sigmoid for an array of values or a list of values. So for starting with the values, it will take more overhead, but for remaining values, they will be able to do it in much lesser time than what we took for calculating one particular value. Next, we are going to see something about decision boundary. Decision boundary is simple. So we are actually proposing a threshold value and we say that if it is over it, it's true. If it is below it, it's false. That's what we are having here. So the code can be very simple. So return 1 if the probability is greater than or equal to the threshold value, else give me 0. Let's do our magic now. Before we start with our prediction, we have now know the value of sigmoid function and decision boundaries. So a prediction function in logistic regression returns the probability of our observation. It can be either positive or negative, so true or false. So let's call this class as a notation p of class equal to 1. So as the probability gets closer to 1, our model is more confident that the observation is in class 1. Let's borrow the equation from linear regression. So our output function can be given by adding the weights along with the classes that we have. So now let us try transforming the output using the sigmoid function to return a probability value between 0 and 1. So when we code this, we will write a class with features and weights, and we do the dot function from NumPy library. Please don't forget to add or import NumPy as NP in your code. So we will get the probabilities as the output for this function. Now, cost function. If you remember, in linear regression, we would have used MSE, mean square error, as our cost function. But we cannot do the same here. We have to include something else. So, if our cost function has many local minimums, gradient descent may not find the optimal global minimum. So here, instead of the mean square error, we use a cost function called cross entropy, also known as log loss function. So cross entropy loss can be divided into two separate cost functions, one for y equal to 1 and one for y equal to 0, as we know. So the benefits of taking the logarithm here reveal themselves when you look at the cost functions in the graphs. For y equal to 1, you can see how the smooth monotonic functions are always increasing or always decreasing. So it makes it easier to calculate the gradient and the minimum cost. The key thing to note here is the cost function penalizes confidence and wrong predictions more than it rewards the confidence and the right predictions. The corollary here declares that the increasing prediction accuracy has diminishing returns on reducing the cost due to the logistic nature of the cost function. Okay, let's see how we can code the cost function. So we can get an equation for our final cost function by combining the two equations where one is for y is equal to 1 and one is for y equal to 0. So j of theta gives us the final, so the j of theta gives us the final cost. And here you can see m, which denotes the number of training samples that we supply. So here we are just translating this mathematical function into code using various NumPy functions. Now let's see about gradient descent. So to minimize our cost, we can use gradient descent. There are so many other sophisticated ways to do this, but we need not to worry about it now. The libraries like scikit-learn and other libraries which supplies the logistic regression function will have their own implementation, so we can focus more on the interesting things like what the data is revealing to us. Here is the code for gradient descent. So we have features, labels, weights and the learning rate here. And n is the number of features. So here we get the gradient and then we are taking the average and multiplying it with the learning rate, which will give us the weights which we can use later. Let's write our final piece of code. First, we have to train our model. So here we write a class for the train and we supply it with features, labels and weights. Wait, we have not declared the hyperparameters learning rate and number of iterations yet. We have to do it prior. So LR refers to the learning rate and iters refers to the number of iterations. So we are assigning an array for the course history, and for every iteration we do the same thing again and again till the point when we reach an acceptable error threshold or when subsequent training iterations fail to reduce our cost. Next, we define the classify class. So here we supply the predictions and we get the classification back, and we write another class that's called accuracy to get the prediction accuracy or the prediction probability of our classification. Now we have all the essential classes that we will need to do a logistic regression. Now let's do a comparison. Let's import the scikit-learn libraries for logistic regression and first normalize it, extract the features, pre-process the data and do the logistic regression. It's very simple, right? If you are using the external libraries, life is much easier. But we just did all the implementation to know how the logistic regression works. So now we are going to compare our accuracy with that. Now we have all the classes that are needed to do a logistic regression ourselves. Let's apply all these classes on a data set and compare our scores. Please select a data set of your choice and apply logistic regression over it to do classification. And comment your experiences down along with your code in the GitHub library. The top 3 will get a shout out in the next video. That's it, we are done. If you want to do more, let's go with neural network, because logistic regression is a neural net with no hidden layer essentially, right? Thanks for watching this video. Please comment for any doubts.